Hello, F Sharp. We are back. I was away for a little bit, went away from my company's conference, and it was actually kind of exciting because I was presenting the engine that this topological sort is used inside of. And there's a lot of excitement around that. So that's really fun. But we are here to continue to optimize this topological sort. Last time, what we left off was using separate stack allocated memory in order to track our progress through the topological sort. Now, today, what we're going to do is something different. We're actually going to be talking through some code that was sent to me by another person in the community. Their name is Denis, and I have their GitHub here. So I'm not sure what this picture is from, but this is what they have on their GitHub profile. But this is Denis. I hope I'm pronouncing that correctly. The American pronunciation would be Denis, but I'm pretty sure that is not the correct pronunciation. So I really appreciated the code that he sent as a way of speeding this up. And so I wanted to talk through what he did to make the topological sort faster. And for perspective, we left off where we got our topological sort of 1,000 graphs down to 624 microseconds. And our goal is ultimately to get it down to 500 microseconds. Once we cross that line, we have success, and now we should go and work on optimizing other pieces of the engine. But that was our goal. We are very close, and I'm excited to show you the enhancements that Denis provided and what the results of that were. So I'm actually going to put these up side by side in hopes that we can kind of go back and forth. Oh, let's see, it might be better. Well, we're just going to do it. No, that's not what I wanted. So I'm just going to do this side by side, and we'll just have to do some scrolling. So let's talk about some of the changes that were introduced. Now, the first one has to do with the graph type. And I can go ahead and zoom in here more. So the graph in version 9, come down to it, is an F-sharp record. And an F-sharp record is a reference type. And that means when you pass it, and that also means that it's allocated on the heap. So when you pass it around, what you're actually passing around is a reference to this piece of memory on the heap. Now, in the code that Denis provided, he added this attribute, which is struct, which is saying, hey, I don't want you to allocate this as an object on the heap. I want you to treat this as a struct. And that means when you pass it around, you're actually passing around the entire thing, in this case, it would be all of these references. And the reason I'm not saying is, and people often say like, oh, well, structs are just allocated on the stack and references are allocated on the heap. That's not that is an oversimplification. I think that's how I would put it, because it is entirely possible for structs to be on the heap because they could be contained in some collection. Like if an array is allocated on the heap, if that array is made up of structs, then like that's a struct and it's on the heap. So I think that idea of saying like, oh, a struct is just something allocated on the stack, that's an oversimplification. I think it's better to think about the memory layout of it and how it is passed around between functions and methods and the impact it has on the garbage collector. Because a struct does not need to be tracked by the garbage collector. And so when you create structs or you pass structs around, there's no references that the garbage collector needs to keep track of. And so it's less work for the runtime to keep track of structs. So that's how I actually like to think of these things. Take it or leave it. So first big thing that is different is that graph is now a struct. Everything else went, okay, so that's the first big difference. Now we're going to scroll down. And one of the other things is that instead of having these separate types, which let me come down up to here. So here I use this type, which is an edge tracker. And this was something that was used to keep track of what edges are still in the graph or not. Instead, and there's some logic embedded here as far as adding and removing. Instead, what Denis does is put all of that in the graph module and in the graph type. And if we come down here, the graph type, we have add to tracker, remove from tracker, tracker not contain, tracker count. So instead of having this edge tracker type, that's all been gotten rid of. And instead what he has is he has a class with a bunch of static members that are inlined, and the tracker now is just a span. So what edge tracker in version 9 contained an array of unsigned int64s, and that's what it was using as kind of like a bit array of sorts to keep track of, is this edge in here or not? What is being done here is like, okay, we're not going to declare another type. We're just going to use the raw span, and we're just going to pass the span around everywhere. So that's the first thing. That is a big difference. And so like fewer types, again, this edge tracker here, this is a class. This is allocated on the heap. And so this is susceptible to heap fragmentation and going in and out of cache. And so this provides some nice abstraction. But if you're going for all out performance, having additional things on the heap might cause you problems. Again, it really kind of depends on the scenario, whether like the nice abstraction is more important to you versus just raw performance. And we're in the situation where like, hey, we still need to go a little bit faster. And so that kind of justifies us like, okay, let's push it to the limit. We're going to have to remove abstraction and get down to the raw computation that actually represents our problem. And so gone is the edge tracker. Instead, we're just using a span, and we are calling these add to, remove from, contains checks. We're using static members that are inlined. And what does that mean? So what it means is that we are inlining this code. We're telling the F# compiler like, hey, I don't want you to like call another method and add another stack frame to the call stack. I want you to take this code and inline it wherever it is used. Now, there are advantages and disadvantages to this. There can be significant speed performance boosts because every time you have a new stack frame, the runtime is having to copy some values on the stack, and that takes time. That's not free. It's incredibly fast, but it is not free. And so we are removing that work from every single call. Now, the .NET runtime and the CLR will analyze your code, and if methods are small, it might just do this for you automatically, which is why like, oh, I want everything to go fast, so I'm going to add inline to this stuff, and you see no performance difference. It's because the CLR may be doing it for you already. So it's not this magic pixie dust you can just sprinkle on your methods and now everything's suddenly better. So this is why it's so important to benchmark and test and verify, because you might be trying to do things that are having essentially no effect on the code. But inlining is a way of saying, is aggressively saying, hey, F# compiler, you need to inline this code. And that's fine. And I use this all the time when I have these, when I have small methods like this, or I have methods that are very commonly used, and I know that they are going to be small, typically are going to be small. Inlining is great. Now it makes debugging, it can make debugging more difficult. So again, use caution, but there are a lot of advantages to doing this should your performance scenario require it, but don't just jump to it. So this is another big difference. No longer using the edge tracker collection. And then we have the static member sort. So this is our sort function from earlier, but now it's a method. And this is gonna be a little difficult. I'm gonna try to put these side by side so we can get some kind of comparison. I'm gonna zoom out a little bit. My apologies to you with smaller screens. I will do the best that I can, but I think it's valuable to kind of see this stuff side by side so I can reference back and forth. So right here, this lined up as best we can. And sort. Okay, that's about as close as I think I'm going to get it. So we're going to see on the left is the previous version, and on the right is the code that Denis sent us. And so we see very similar declarations. Hey, we're bringing all of these ranges into kind of our local scope here. Same thing happening here. And then things are a little different. I'm declaring a result array and saying, hey, I want an uninitialized array. Denis is doing the same thing here. And then we're going to iterate through the source ranges, and we are adding those to possible results as far as, hey, these are the nodes that we want to examine. And then things actually kind of significantly change. And so instead of remaining edges, so remember how I instantiated this edge tracker here. So what this is going to do is, in the old code, edge tracker is a class. It's going to be an object. It's allocated on the heap, and inside of it, it is holding an array, which is another heap allocated piece of memory. Instead, what Denis does is saying like, hey, this is just creating the raw span here. So like, hey, how many bits am I going to need? I'm going to declare my remaining edges as an array. And here, what he's using is the GC allocate uninitialized array, which means like, hey, .NET, give me an array. I don't care what raw bits are in there right now. I don't need you to zero it out. I will take care of it. So dangerous if you don't know what you're doing, but very useful if you know that you're going to overwrite every value in there anyway. And then it says like, hey, I want this as a span, so I can pass it around as a span, and then iterates the whole thing and is adding the edges to the tracker to say like, hey, I'm putting all the edges in there for the sake of tracking. It's the same thing as these few lines of code here. We're saying like, hey, I'm adding the remaining edges, but now it's just doing it with the raw span. And the span, as you know, is allocated on the stack. So no GC overhead for that. And then if we come down, the next big difference here is down in this loop, the while target index less than bound. So this is when we've taken a node and we want to look at all the children of that node to see if there's something that we can move to now inside of the cons algorithm. And get this lined up. So I'm gonna have to zoom out a little bit more just so we can see this whole thing just due to indentation. So on the left, we see what the original code was doing and saying like, hey, I'm removing this target edge. I'm removing it, and then I want to get that target node, and then I want to check that nothing else is actually referencing that node. And if nothing else is referencing that node, I'm going to add it to the nodes that I'm going to examine next. And so basically there's just this loop of like, get the target, look, have all of the parents of the target been removed from it? If so, then I want to add it to my results that I'm going to be examining. And the way it's doing it is it's doing the lookup here, and then it's using this range.forAll, which is like, hey, I'm going to go check every value in this range. And so it's going to iterate through several things and check that this condition is true or not. Instead, what Denis does is saying like, hey, I'm going to create this variable, which is no remaining sources result, and it's going to default to true. I'm going to get the range that I'm going to loop through. I have the source index, which is the start of the range, and then I have the bound of the range. And then I'm going to have this while loop. And while source index is less than bound and no remaining sources result is still true, I'm going to continue looping through here. And so what it does is it goes through and it evaluates, hey, graph type dot tracker not contains. It's doing this check, and this means that this loop will do an early termination. So if this ever switches to false, this while loop will stop early, which is different from here because this range is going to check every single value. And I'm going to go ahead and check that. Okay, no, I take that back. So the range for all does also have early termination. But so similar, but not quite the same. Go ahead and go back. So essentially this code is kind of unrolling what is over here. There is another significant difference that I wanted to point out that I thought was really clever, and I wish I had thought of, so I'm going to steal this at some point. You notice what I do here on the left is I say, hey, remaining edges, I want you to remove whatever this target value is. And then you see I want to then now get the target. So whatever it is that I just like removed, I'm now wanting to get that value back out. And what is done here in the new code is that remove logic is also returning the value of what got removed. So it's kind of taking this, it's taking the remove action and the retrieve action, and it's combining them into one thing, because you're having to end up looking up the same bit in the collection that's behind the scenes. But in the left, it's having to do it twice, and on the right, it's only having to do it a single time. So that's a clever optimization to say like, hey, I'm having to do this work already, so I'm going to combine it to see that it's faster. And then as far as the rest of the code, oh, and there's one other thing I wanted to point out. So here, the graph, remember the graph is a struct here on the right. Normally what you would do is when you pass a struct to a method or to a function, you're having to copy the entire thing. You're operating like, so it's like, if it's just an int, it's not a big deal because copying the value of an int is like essentially free. It's a single operation. But when you have a struct and there's multiple fields in there, you're having to copy the value of all those fields anytime that you're passing it to something else. Now that's less than ideal. Well, that's fine. It still can be very fast, but as your struct gets larger, the amount of time it takes to copy that memory goes up and up and up. So that's less than ideal. So there's a way around that, and that is using inrefs, or inref, outref, or byref. And again, in F#, this is kind of, now that we're kind of getting into the really nitty gritty of F# performance related code, passing things by ref is a way of saying like, hey, I don't want to actually copy all these values. I just want to give you a reference to where that memory is on the stack. And that's just what this is doing here, saying like, hey, when you call sort, it's not copying the entire graph for you. What it's doing is it's giving you a reference to that graph for you to be able to use. And so you avoid the cost of copying the entire struct. And so that's one way you can kind of get the performance of passing around a ref type without if you have a struct, you can get the performance of passing around a ref type without actually having to copy the entire struct and paying that penalty of copying everything. So this again is another kind of optimization in terms of reducing the amount of work that the CPU is having to do in order to pass these values around. So lots of little clever little optimizations in here, and it just kind of again shows like, man, no matter how much you think like you've optimized something, there's always like, oh yeah, like why am I doing that twice? And so like one of the things that I would take away from this is like when you get down to this level of code, just like ask yourself, am I doing anything more than I need to do? Am I doing anything twice? Am I accessing the same piece of memory multiple times when I could just access it once and do everything I need to do with that piece of memory and then go back to the work that I was doing instead of having to go back to it multiple times? And so, like I said, some really clever optimizations in here and bears some pretty significant fruit. And so when we run this version of it, let me go ahead and zoom in. The version 9 that I had, this is the best that I had gotten to this point, was 607 microseconds. Denis's code got down to 570 microseconds. So very impressive. We also see that there's fewer branch instructions overall, fewer branch mispredictions, and fewer cache misses. So all around, some really good stuff, and less is allocated. So we're going to have less impact on the GC. So some really good stuff. I really appreciated this pull request. It was really fun looking at it and kind of going back and forth and looking at the performance differences. So yeah, really exciting. So I hope you found this interesting and useful. We got 2 more versions to go before we get to the ultimate version of this algorithm. I really appreciate you taking the time to hang out with me and talk about some high performance F#. Thank you very much. You have a great day.